This is the table of contents for the How We Got Here section. Again, this section goes through the greenhouse effect, comparing human versus natural carbon emissions, and then analyzing the impact of those changes on Earth's climate. The key argument for this section is that human fossil fuel use has destabilized the natural, delicate carbon balance on Earth, heating our climate at an unprecedented pace. Let's start with one of the most important processes that shapes Earth's climate, the greenhouse effect. Greenhouse gases act a bit like a one-way door. They let more energy enter Earth's atmosphere than they allow to escape. So let's break down how that works. The sun emits a broad spectrum of different types of light, but here we're going to focus on the visible light that comes from the sun, because visible sunlight has a bit of a diplomatic passport. It's able to pass straight through the atmosphere without interacting with any of the gases that are there. And so it comes straight to the ground, and once it hits the ground, or anything in the way, some is reflected, and it stays visible light, but some is converted to infrared light. And infrared light is a different part of the spectrum. Human eyes aren't able to see it, but we can feel it. If we put our hand near a campfire or a hot stove, it still has energy retained as heat. And so once that visible light and that infrared light are both heading up through the atmosphere, they have a very different path from there. Because the visible sunlight keeps that diplomatic passport, it passes straight through again, and it escapes to space, gone from Earth's atmosphere forever. The infrared light, on the other hand, is able to interact with a class of molecules in the atmosphere called greenhouse gases. And these are carbon dioxide, water vapor, methane. There are some others as well. Because of the way these molecules are structured, when a greenhouse gas molecule is hit by an infrared photon, they're able to absorb its energy and then to re-emit that energy in a random direction. So infrared light can escape to space again, but if it does, it's probably taken a much longer path, bouncing between greenhouse gas molecules. And so as a result, the more greenhouse gases you have in the atmosphere, the more of this heat is being retained and bounced around, and as long as it's staying, that energy is remaining as heat within Earth's atmosphere, making the climate warmer. Given this effect, greenhouse gases can be thought of almost as Earth's thermostat, shaping the climate over the planet's history. So if we take the pre-industrial average temperature as our baseline, let's look first at times when Earth has been colder than that. The most recent one was the last ice age, when much lower carbon dioxide resulted in the planet being about 4 degrees Celsius colder on average. There are many trends that helped end the ice age, but one of them was large-scale emissions of carbon dioxide. There's been even more extreme cases. There's evidence for the thesis of snowball Earth, in which Earth's interior actually absorbed a lot of carbon dioxide from the atmosphere, resulting in such a weak greenhouse effect that the planet was vastly colder and was covered in glaciers. So it really goes to show that the greenhouse effect is not necessarily bad. It's a very important factor in keeping Earth's surface warm and habitable. The only issue is that we've been pushing it in the opposite direction. So right now, we have warmed Earth by about 1 degree Celsius from the pre-industrial age, after raising atmospheric CO2 by about a third since then. Actually, at the last time Earth was at today's carbon dioxide level naturally was about 3 million years ago, and it was 3 degrees Celsius warmer on average, and also the oceans were over 50 feet higher. Now that is not going to happen tomorrow. It takes a very long time for Earth to fully adjust to a shift in heating. But that is the long-term path that we're on if we continue rates of fossil fuel burning that we're at now. More extreme examples include the Earth in the Eocene era, when very high carbon dioxide made the planet so warm that if you look at this image closely, in this climate, Australia and Antarctica are those green forested islands, just to give a sense for how different that climate was from the one that we have today. And then finally, in the most extreme scenario, not that we would ever try to make this happen, but Scientists have estimated that if we burned all known fossil fuels, we would warm the Earth by about 10 degrees Celsius. Given how huge a role carbon dioxide plays in shaping Earth's climate, let's talk about the ways that it cycles in and out of the atmosphere. So, carbon naturally shifts between the atmosphere, where it's stored as carbon dioxide gas, and the interior, where it's stored within rocks, within fossil fuels, within many other storage methods. Carbon can cycle from the interior to the atmosphere through volcanic eruptions, and it can return from the atmosphere to the interior through a process called weathering, in which carbon dioxide is dissolved in rain, forms in the ocean into chemical compounds that can sink to the seafloor and be compressed into rock layers, rejoining the crust of the Earth. Now, that natural cycle exchanges around 0.1 gigatons per year. Gigaton is 1 billion metric tons. As we covered, there have been periods in Earth's history where that cycle gets very unbalanced. Periods when you have massive volcanic eruptions for periods of time that really elevate the level of carbon dioxide and cause a lot of heating, and even times when weathering really picks up and actually cools the planet down by withdrawing a lot of carbon dioxide. But for recent history, until humans showed up, basically this cycle was, about 1/10 of a gigaton per year being emitted, and then about 1/10 of a gigaton per year being taken out in balance. In comparison, humans, by burning fossil fuels, are currently emitting about 10 gigatons per year of carbon into the atmosphere. That's 100 times that natural cycle rate. And let's talk about what fossil fuels are. Fossil fuels are dead plants and animals that, if they died and sunk to the bottom of oceans and swamps, and if the ground shifted so that biological material was pushed underground, they can, over hundreds of millions of years, be compressed under intense pressure and intense heat, and that biological material can be turned into coal, oil, or natural gas. Now, when we extract those fuels and burn them, they're really powerful because they contain all of the biological energy that was compressed from those dead plants and animals. The problem is that they also contain all of the carbon that was within those dead plants and animals. So what we're effectively doing by burning fossil fuels is extracting the energy and the carbon from hundreds of millions of years of life on Earth and emitting it all of a sudden over the course of a couple of centuries. Now, out of that 10 gigatons per year, about 5 gigatons per year are being taken away by extra absorption from soil, plants, and the ocean. They're really taking one for the team and suffering major consequences, especially in the ocean. We will talk about those on a later slide. Even with that extra help, we're still adding about 5 gigatons per year to the atmosphere every year. And so as a result of that unbalance, atmospheric carbon has gone from about 600 gigatons in the pre-industrial age to about 870 gigatons and fast rising today. Let's zoom out a bit to see how this massive surge in emission looks on the scale of recent history on Earth. This chart shows the atmospheric carbon dioxide in blue against changes in temperature in Antarctica in brown. And humans emerged about halfway through this 800,000 year history. So the two track each other pretty closely, and until the modern era, the highest that carbon dioxide had been was about 300 parts per million. And parts per million just means that out of every 1 million molecules of gas in the atmosphere, how many of them are carbon? So again, until the modern era, a maximum of about 300. Today, we are here at an average level of 410 parts per million. We are raising carbon dioxide so quickly that on this time scale, the chart looks vertical. And there's another way that I like to look at this in terms of who is winning in the race for all-time carbon dioxide emissions records of Team Human versus Team Nature. Now, first up, Team Nature. Let's look at what nature can bring to the table. Looking for the most extreme known natural heating event in Earth's history points us to the Paleocene-Eocene thermal maximum, about 55 million years ago. Scary name for an event that must have been terrifying for anything living on Earth at the time. There are debates over how exactly this worked. Some of them believe that methane played a major role. But if carbon dioxide was the main driver for this event, then even with that assumption, the highest that carbon dioxide emissions could have been was about 0.2 to 0.7 ppm per year, at least doubling carbon dioxide over 6,000 years, which on a natural time scale is an extremely fast period of time. Now, in comparison, what are we doing? I'm very proud of the little trophy I gave us here because we are absolutely winning this race. We are currently adding around 2.4 ppm per year of carbon dioxide to the atmosphere, putting us on pace to double carbon dioxide over 150 years, a fraction of the time that most extreme natural event took. Now, if this rate has happened before in the history of Earth, it was probably over 750 million years ago, before complex animals evolved. And that's because before then, there's not much of a scientific record for us to go on for this kind of event. But we can't find evidence for something more extreme than the Paleocene-Eocene thermal maximum within the last 750 million years of life on this planet. Since it's so hard to visualize human emissions on this timescale, let's zoom into only the human era to try to get a better handle on it. So this chart on the left shows total atmospheric carbon dioxide levels in ppm. And the last ice age was 185. The pre-industrial era was 280. So over 20,000 years, about 95 ppm of natural emissions were enough to shift the climate from one in which a large portion of the Earth was under glaciers to what the pre-industrial era was. And so let's now look at what humans have been doing. As you can see, we are not only in 2020 further away from the pre-industrial era's level of CO2 than the pre-industrial era was from the last ice age, which when I found it out, I was horrified by. But those dots are getting further and further apart. We are not just making this problem worse, we are making it worse faster and faster. And if we continue to emit at the rate that we were in 2019, then that dot in 2040 is going to be even further away from where we are now than any of those previous gaps have been before. So just watching this period of 60 years when humans matched the total natural emissions that took 20,000 years to shift the Earth from the last ice age to that pre-industrial era gives you a sense for the danger that we are in. And let's look at what this means for living on the surface of Earth. This is a graph of the global temperature change for the last 140 years. Its baseline is the difference, is the 1951 to 1980 average temperature. So anything on the left side in blue is cooler than that baseline. Anything on the right is warmer. And so as you can see, there is some year-to-year variation, but the trend is extremely clear. The Earth has gone from being cooler than that baseline to being much warmer than that baseline, getting warmer faster and faster. And if you want to see what the warmest 6 years in recorded history have been, you don't need to look far. They're the last 6 years. This chart on the left, seeing that today's carbon dioxide level is further away from that of the pre-industrial era by more than the pre-industrial era is from the last ice age, is what really started to scare me and really started to get me to dive fully into this research. And you might say, as I did at the beginning, that if this threat is so clear, and having such an obvious impact, then the governments and international organizations of the world must be putting in place a plan to address it. And they're trying, but so far they're failing. Let's start here by looking at this chart on the bottom. Now this shows, in that black line on the left, actual emissions from 1990 to 2014. And then the arcs from there are based on a study that looked at the pathways that we could take from that point. So if we managed to cut emissions enough to stay within that blue range, we would be on track for about 2 degrees Celsius of warming by 2100. If we managed to cut even further and be in that green range, we would be on track for 1.5 degrees Celsius. And now those are the amounts of warming that the Paris Accord, in theory, promises. Now the Paris Accord is still the most comprehensive international climate agreement in history. It was signed in 2015. Almost every country on Earth agreed to its binding pledge to limit average global temperature rise to 1.5 degrees to 2 degrees Celsius above pre-industrial temperatures. Now those increases are not safe. They are still going to have major consequences, but they are a point where scientists agree we can try to draw the line and hold it to avert even more uncertain and catastrophic damage. Unfortunately, we're not on path for that. Optimistically, the Paris Accord is going to get us in that orange range, because despite the pledge that countries made, the actual individual plans for emissions cuts, if you add them all up, are not enough even to hold us to 2 degrees Celsius. Even if all of the plans are fully met, and that includes meeting a lot of promises and allocating a lot of funding that have not yet been followed through on, temperature is projected to rise by 2.5 degrees Celsius to 2.8 degrees Celsius by 2100. And that might not seem like that much more, but the consequences of warming, which we're going to talk about in the next section, compound on themselves and get higher and higher at a faster rate the more warming happens. So there is a serious gap between 1.5 degrees and 2 degrees, and then between 2 degrees and all of the values that are higher than that. And that is bad news, but there's worse news because we're not even on track for that. Many signatories to the Paris Accord are failing to meet their national plans, which were already insufficient. And if we continue on that path, we're in the red range. We're going to see temperatures rise by about 2.8 degrees to 3.2 degrees Celsius by 2100. And in the next section, we're going to talk about what that means for life on the surface of Earth.